you've come across this idea of what's called a piecewise function before. You've all dealt with it. For example, if you go to the movie theater, you pay a certain fee for certain ages. Up until 12, let's say up until 12 years old, you pay $6 for a movie. Between 12 to senior citizen, you pay $10, and at senior citizen, you go back down to $8. So there are certain values which you have to pay for your costs. Okay. Same idea with like car insurance. Car insurance, when you're 16, a 16-year-old male in car insurance, disregard the style of car, obviously, for this purpose. You're paying more for car insurance 16, 17, 18 years old until you turn about 25, and then it tends to go lower. You get married, it tends to go lower. As you get family, it tends to go lower. So you get stuff like that. So it's on a, you ever heard the term sliding scale? That's kind of what it is. Health insurance. You'll hear people about getting life, and you've heard commercials on the radio about life insurance. A person that is 60 years old, non-smoker, on diabetes medication, gets life insurance for $12 a month. Things like that. Certain things are weighted into it. That's pretty good, wasn't it? So you get stuff like that. But the idea here is when we're looking at these are actually called piecewise functions. Piecewise functions are functions that are dependent upon the domain. Now, if you recall, domain stood for which values? The x ones or the y's? The x, because what comes first in the alphabet? Domain or range? Domain, which comes first, x or y? All right, another step of that. What comes first in the alphabet? Horizontal or vertical? Horizontal. There's a reason why I'm saying that, because you'll see it as we go along. Now, real simple example here, and I don't want you to write this out. I don't want you to draw it. I don't want you to do anything, but just look at it. Do you guys agree that there are two distinct lines here? They change where? And they happen to change at the origin. They change at the x value of 0. The domain changes the function when it reaches 0. Okay? Now, if I'm looking at this graph, we should be able to look at the graph and figure out what each of the equations of the graph is, shouldn't we? We could count slopes and do stuff like that. So, first of all, I'm looking at this curve on the left. Is that a positive or a negative slope? Positive. What is it? Yeah, very good. It's a slope of 1. It goes to the origin, so it's y equals x. So my first equation, I would say, is y equals x. Now, that equation is increasing from left to right. When it's increasing from left to right, what's to the left of it? Is there a known value to the left of it? Do the numbers on the left ever stop? Are the numbers to the left of 0 positive or negative? Negative. So I could say this is increasing from negative infinity to 0. So this graph will always occur when values of your domain is less than 0. You okay with that? Yeah. Now, it'll become more clear as far as whether or not it's going to be a less than or a greater than or a less than or equal to or greater than or equal to as we go along. But I just want to show you what it looks like, how domains change, all right, how the ranges change in relationship to the domain. Now, to the right of 0, the slope changed, didn't it? What's the slope become now? 2. So the equation to the after you hit 0 is y equals 2x. And for argument's sake, I'm going to say that when x is greater than or equal to 0, it switches graphs. So depending upon what your input is, your output is going to be different. There's a lot of that. Okay? Now, if somebody was chasing them with the machete, I'd be like, weird. We'll come back. So, I want you to think of this. Remember Plinko? All right, Plinko. Exactly. You have a wooden board, like a small disc. You drop it in, you win $2,000. What's that? Plinko, it's on The Price is Right. All right. It's you put into the function machine, you drop the Plinko chip, and it went down the Plinko machine. At the very end, it fell into some domain which you won a new car. Now, yeah. Do you know what that stands for? Function of x. Very good. F of x is how you would say that. F of x equals function of x. Now, you've probably done this as well. Not graphically, but algebraically. What's f of 7? What's f of 7? What is that 7? What is it telling you to do with that 7? Remember what that meant? Replace it with x. Good. That means wherever I see an x, I'm going to replace it with a 7. But I have to make a decision. Is that value of 7 is a domain because it's an x value. I have to figure out which function do I substitute the 7 in. So the function itself is restricted by the domain. The domain is restricting your round value of 2. If my value of x that I'm substituting in, my domain I'm substituting in my function is smaller than 2, I use the top equation. If my domain value that I'm substituting in is greater than or equal to 2, I put it in the bottom equation. So with 7, is it smaller than 2 or greater than or equal to 2? Which means in my function machine, my Plinko machine here, that means I'm going to do this. 2 times 7 plus 1, and I get 15. Okay? These types of problems were when you first learned about what's called function notation. F of x, g of x, f of g of x. You might have done compositive functions. You might not have done compositive functions. We will do those at some point this semester. This is just a little brief reintroduction of it, because I found that if you see this again, you're like, oh yeah, on one side you do this, the other side you do that. Okay. All right. Now, if I say f of -3, which one do I use? Top equation or bottom equation? And why is that? Ding, 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 ding. So that means I get -3 plus 2, otherwise known as, try to do that better, -1. So when you do this algebraically, they might just say, hey, what's f of 12? And then you have to go, 12 bigger than 2 or smaller than 2? Hold on. Take off my shoe. Unless you're wearing sandals, then you're fine. Unless the number's over 20, then you're really. Unless you're Antonio Alfonseca, he had an extra finger. It was a picture for the Cubs. He had 6 fingers. Okay, he had 6 fingers on his glove hand. He had 6 fingers. Anyway, so what would you do then? Let me show you what we would do if we had to graph this. Now, normally I don't like getting out graph paper or using graph paper, but this is one of those sections that I found that actually having a piece of graph paper is kind of nice. So, do me a favor, take 2, one for a couple of the examples we're doing in class, and then one for some homework files I can do this evening. You can use yours, it's fine. You got it. That's fine. If not, no problem. We don't like it. We out. What do I need more? we do really like you. Do you need another one? He's got two. See, a true gentleman would have given up his graph paper. You guys you need some? Stay out, senor. All right, anywho. So now, when we graph piecewise functions, especially usually the first couple that I ever do with students, I like to really oversimplify. So in doing so, I look at my function that I'm given, and then in my function, you'll notice that there is some domain restriction given. What I mean by that is, where's something funky going to happen? 2. The reason why I'm saying that is that if you look at it, it's telling you use this graph when x is smaller than 2, use this graph when x is bigger or equal to 2, which means something weird is going to happen around the number 2 for the domain. So what I do is, since I'm looking at a domain, that's my x value, I'm going to draw in a lightly shaded vertical line at 2. That way I know that when I'm graphing this, to pay attention to what's happening on either side. I don't know what side I'm going to have to graph it for, but I'm just going to put it there to begin with. And now I just go about graphing like I would normally. When I have f of x equals x plus 2, where do I start that graph? At positive 2, and what's my slope? 1. So I start my slope at 2. I'm sorry, start my graph at 2, and just walk my slope. With these, I will probably overdraw the whole graph first couple of times, because then I can go back and erase what I don't need. Right now, I have graphed the entire graph paper of the equation x plus 2. But according to my domain restriction, I only need to look at this graph when x is less than 2. So do I need any of those dots to the right of that semi-drawn vertical line? Nope. So I'm just going to go back and erase them real quick. Later on, you probably won't even need to bother doing that. But for the first few, I'm just going to, it's kind of nice to oversee what you're doing. Now, think about all the times we've dealt with inequalities. When we dealt with inequalities, at the value of 2, it says x is less than 2. So at just this point, should this be a solid or an open dot? It should be open. So here's what I do. I've already made a little bit of a dot there. So what I like to do is just kind of over-exaggerate and put a big circle around it. It just makes it evident that it's going to be an open dot. And then I connect all the rest of them going to the left. That graph is done. I domain restricted x plus 2, and I only graphed it for all values of x such that x is less than 2. That's fancy. Dotted lines are when you're doing the whole y is less than or equal to. This is just f of x equals x plus 2. Okay? It's a very common question. You only deal with that when you have the inequalities of the two variables set. Go to the next graph. 2x plus 1. What do I start that graph at? At plus 1. So if I start that at plus 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Oop. Do I need to finish that graph to the left? No, because I know that I'm only looking at that graph going off to the right. So when x was equal to 2 on this value, I should have gotten 5. Did my dot line land on 5 when x is equal to 2? Yeah, that's a good sign. So I'm going to go back and erase these little ones here. Well, that one's not bad. It's kind of just covered up already. Here, I'm just going to kind of make this a little bit larger of a dot, just to show that it's starting there. And which way do I connect it? Going up. It changes direction. It changes the range. The function itself changes at. It was increasing at a slope of 1. When it got to 2, it's increasing at a slope of 2. What's that? Think of it as a jump. All right, think of it as a jump. If I get this out of the way, you'll see that you have a small break. There is no range values between 4 and 5. There's no value that's going to give us 4.2, 4.3. None of those are going to work. When x is getting closer and closer to 2, once it reaches 2, it's not going to equal 4. It's going to equal 5. It just jumps. All right. Let's try another one. Let's try another one. I'm going to make this second graph a negative slope, just so to kind of show you that it can do something different. So I have f of x is 2x minus 1 if x is less than or equal to 1. And then f of x will equal negative 3x plus 1 when x is greater than 1. Normally, yes, you're going to have one or the other. It is possible to have them both greater than or one less than. It could be less than 1 or greater than 1, which means it's never equal to 1. Think of that as, what can't that be? 0. Okay, that can't be 0, but it could be really, really close to negative, like a negative 0.00001, or it could be 0.00001. Same idea if I put this, I can get really, really close to 1, but it doesn't have to, it can't be 1. I'm plus or minus. Does that make sense? So you could have that, but here, more often than not, you'll have something like that. And there's a couple examples that I'll have later on where there are just open circles. Where's something funky going to happen? 1. So just out of the top of my mind, I know that something weird is going to happen around 1, so I might just put a little line here to remind myself that something's happening here. 2x minus 1. Where do I start that graph? At negative 1. Good. So I start at negative 1. My slope is 2, so I go up 2 over 1. And then right away, I hit that barrier line. I know that it's got to be less than or equal to, so I know that it's going to be a solid dot here. But numbers that are less than or equal to 1, do I continue to the right, or do I just work backwards? Let's work backwards. So I know that I hit that wall. I stopped and said, okay, something funky happened. Let's figure out what the funky happened. And now I'm going to work backwards. That was good. And I was just listening to James Brown getting funky with it, too. So there's that. It's all a funky good time. I'm sorry. I never really said I was funny. And the graph is going that direction. So far, so good? Okay. Now, I go to my second graph. Well, this is really cool if you've got 2 colors. Go ahead and use 2 colors. If not, it's no big deal. Next graph says to start it at positive 1. And I have to do a slope of down 3, right 1, down 3, right 1, and so on. And notice how I knew to put an open circle on that right away? Because I knew that it was domain restricted, that I'm looking for all values of x for this graph that are greater than 1. Yes, sir? The first one was 2x minus 1. Are you thinking because it's just moving this way? Isn't up and right the same as down and left? The slope is still 2. So if I go down 2, it's negative. If I go left 1, it's negative. Negative divided by negative is always positive. Is that what you're getting at? What was it? Never mind that. All right, so back on this one, I have a slope of negative 3. That's why I started at positive 1. I don't need that dot there, so I'm going to get rid of it. So I have an open circle at 1 because it says it's an open circle, and I'm continuing to the right. And I just connect the dots. And there's your piecewise graph. It's pieces of graphs is really all it is. You're basically graphing 2 things on a piece of paper and going back and erasing where it doesn't occur. It's restricted because of the domain. The domain are the x values telling you where it's going to happen. Okay? Absolutely. Yep. And you can have something that plateaus. You can have, actually, we're going to talk about something that's completely different. We're going to talk about something that's called a step function. Step functions are basically the idea of pay as you go. Student loans. Student loans can be repaid back at certain different values. If you make a certain amount of money, you pay a certain amount of percentage. You make the next certain amount of money, you pay a different percentage. A certain amount of money, different percentages. So if you have value, each step up changes the range. Bless you. Kids between the ages of 0 and 5 are free. At 5 to 7, you pay $3. From 7 to 10, you pay $5. From 10 to 15, you pay $12, and so on. So you have certain values that changes prices. It's step increases. It looks like this. Oh, actually, we'll do a step and we'll come back to that. This is called a step. Bless you. A step function. Steps, if you don't want to die, are usually horizontal to the ground, aren't they? Because if steps were vertical, it's really tough to walk up a step, isn't it? I mean, I guess we're standing vertically as we're walking up horizontal steps. So if we were standing horizontally to horizontal steps, wouldn't we be working vertically? I know, right? I think I confused myself. Steps. When you graph these, it's going to wind up being a bunch of horizontal lines. Remember, y equals a number is always a horizontal line. This domain restriction is telling you how long that horizontal line will be. So at y equals 1, line at 1. Y equals 2, it's a line at 2, 3, 4, and so on. The domain then tells you open or close dots for however long the duration of time it is. So when you graph this, y equals 1, horizontal line through 1, where does it start at, according to the domain? At 0. At 0, is it an open or a closed dot? Closed, because it's 0 is less than or equal to x, but x is less than 1. Solid, open, connect the dots. What happens when x equals 2? I'm sorry, when x equals 1, it goes up the spot. Solid, open. Solid, open. Step functions just look like that. They're steps. Do they have to be equal distance heights-wise or length-wise for the step themselves? No. y equals a number. And remember, f of x is synonymous with y equals. So if I see f of x equals 1, that just means this is a horizontal line through 1. If I see f of x equals 2, it's horizontal through 2. Yeah. F of x equals and y equals are synonymous with one another. Function of x, y equals, these guys be functions. Okay. The other one was vertical because we knew something funky was happening at the domain restriction. I could put that in here as well. I know that something funky happens at 0, something funky happens at 1, something funky happens at 2, 3, and 4, and all I've done is I've filled in what was going on. But with these step functions, these guys are just horizontal lines. I don't need to put all those extra pieces to it. If you want to, go for it. I think step ones, they just get messy. Right? That's something new, isn't it? Was it tough though? All right, I got another one. We'll try one more of those real quick. So we got plenty of time today. So yeah, f of x is either 4, 5, or 6, and it's restricted if it's 4 between 0 and 2, including 0, excluding 2. Sorry, I get ahead of you. I don't need to. I'll let you guys write that out first. So let's see. Am I including 0 or excluding 0? Including. Between 0 and 2, where do I put my horizontal line? 4, very good. Cinco. But you give up already on counting? Get us up at 5? Jeez. Now what happens when it hits 2? What does the step function jump to? Goes to 5. It includes 2, it excludes 4. Between 2 and 4, it's equal to 5. And then between 4 and 6, it equals to 6. So think of it this way. It's $4. Correct. That's what that means. Does that make more sense if you see it written like that? If you relate it back to money, and if you think about it, your parents at some point probably played this game, where you might be 4.5, but you might be short. Oh, they're almost 4. They might save $1 or $2. It's very true. Yes, but we did that with our youngest. Well, actually, our oldest we were able to do that for a little bit easier. Connor, he was born rather tall and everything, but he was always when he was 2, 3 years old, he was always still a little bit. He was a little bit shorter. But then he gets growth spurt. He's huge now. But so oh yeah, cheaper. But he's 9 now. But our youngest, Moose, when he was born, his name is Moose. When he was born, his head was the size of his shoulders. So, yeah, Moose has always been. We weren't able to play the game of, oh yeah, he's 4. Moose is Moose. It's going to be interesting to see. Both of our kids have been on the top end of height charts and stuff like that, and for about past 4 or 5 generations of Murphys, the sons have always been taller than their fathers. I'm 6'3", so I'm going to be really interested. Our pediatrician says that Moose is going to have absolutely no problem passing me up. So children are going to eat me out of house and home. They are. They're going to get big. Moose, he loves playing soccer. And when he's playing soccer, he's in the age group, first, second graders, kindergarten, right there. And he's turned into like a natural defender. I don't know. My wife played soccer for a long time. I never played a day of soccer in my life. And so he got all the soccer genes from her. And he gets out there and he already knows how to cut the angle to block people out. And being a bigger guy, people are flailing off him. It's pretty funny. So. He's fast too. So anyway, does this help a little bit? The idea, if I relate it back to money, it helps out a lot, I think, to see how it breaks itself. Now, one other quick style before I let you go on some problems was this one. Sometimes you're only looking for a chunk of a function. We're not looking for the continuance to negative infinity or the continuance to positive infinity. We're looking for the function just to occur within a specific parameter. Very similar to what we did with the step function, but the step functions were always horizontal. These guys still have slopes. Horizontal has slopes too, 0. These guys we're going to look at, we're basically graphing segments here. Whereas earlier when we had things dropping off towards infinity, either negative or positive, you're kind of graphing rays. If you want to relate it back to geometry terms. Now, here, I'm going to try and not draw in those verticals and show you how you can do this pretty good ease. First one is 2x plus 1. Real simple. Slope is 2. What's your y-intercept? So I'm going to start at 1, walk my slope of 2. I'm going to go back the other way. And now I'm going to look at my domain restriction. I only want this graph to be graphed between -2 and +6. You okay with that? I want only the domain values of -2 to +6. Do I include -2? Do I include +6? No. So I'm going to look at my graph, find where x is equal to -2, right here. I'll go to here. I'm going to over circle it because it doesn't include. I know I have to go this way. Oh, so I'm going to erase these. But unfortunately, my graph kind of stopped here at 4. So can I just kind of fudge it to figure out where I wind up at 6? Yeah, that's okay. That's good enough for me. Okay? That's good enough for me. You're getting a visual representation of a rough sketch of what this graph is going to look like. That first one is done. The other one has a y-intercept of 0 and a slope of -1. So I'm looking for it to occur only between -8 and -4. Negative slopes go down and to the right. So if I start here, I'm just going to work upward. I'm going to just count to where I get to -4, open circle, and 8, and connect it. I've created basically 2 segments, which is similar to what you did with step functions, but you just have a non-zero slope. Your graphs are domain restricted because of it. Right? You learned something kind of new. What's that? You're having a good time. I sense sarcasm. Stitch. I think, if I'm not mistaken, did I post the numbers of which ones to do yet? Yes. Nothing. Because they're restricted via the domain. It's tough to show. It's tough to show how this works in a piecewise function. It's much easier to explain it when you have step and I throw money at it. It's the same basic idea, but turning it sideways. Just wait. Yeah, it's just little piecewise stuff. Now, did it? If I'm not mistaken, I asked that you guys did. I think it was 21 through 30, and then 35 through 40. Does that sound right? So the graph ones should all, you've got to shoot a graph paper. All the graph ones will fit on there without a problem. And then I've got 6 of them for you to write the equations. Yes, sir. Yeah, go ahead. I think it's just a pass thing or something. Real quick, I wanted to show you, kind of like what he was asking a minute ago. When he was asking a minute ago about how do you know whether or not something's going to have open or closed dots? If you look at number 38, I'll put it up on the board here. If you look at 38, how many different graphs do you see? There's 3 of them. If you look at you'll see that there's one here, and one here. Okay? So that means you're going to have f of x 1, 2, you have 3 different graphs there. Now, do you see any open or closed dots anywhere? No. So when this occurs, like how I would do this, is that I would say that this first graph is a solid dot. The graph between would be open dots. And the graph here would be a solid dot going down. Does that make sense? Yeah. It's kind of, even if you flip them, it doesn't matter. There's no right or wrong answer to that. I think that's kind of what you were alluding to before. It was like, hey, how do you know if it's going to open or close? Yeah. This is kind of like that weird situation that it happens. Because as you get to -2, it switches and goes horizontal. When you get to +2, it drops again. So it's one of those things that you can either say either one, but me, I would say the horizontal chunk would be the opens, the other ones would be the downs. Whereas if you look at the other problems, they have close and opens, close and opens, closed opens, stuff like that. They're very easy to see. That's the only one that doesn't have that. Yes. Yeah. It's one of those things. There's really no right or wrong answer. All right. Super exciting, right? Aren't it just so much fun?